Okay, we can dispose of this question very easily. x3 of t is negative 40 centimeters per second times t plus 20 centimeters per second squared times t squared. x1 of t is 15 centimeters per second squared times t squared. Might be a little hard to read, but we just wrote this down. So we solve this. It's a quadratic function, a quadratic equation. We bring everything over onto one side, subtracting 15 centimeters per second squared from both sides. We end up with only 5 centimeters per second squared times t squared. Subtracting this term from this term. 5 centimeters per second squared times t squared minus 40 centimeters per second squared times t equals 0. Now we could plug this into the quadratic formula, but in this case it's much easier to solve this simply by factoring. We get t multiplied by 5 centimeters per second times t minus 40 centimeters per second equals 0. Now by the zero property of multiplication, this product is 0 if t is 0, this term is 0, or if this term is 0. Okay, well, t equals 0, yes, at t equals 0, the two were at the same position, but this one wasn't even moving, and that's not really a particularly relevant result. Okay. This equation, setting what's inside the parentheses equal to 0, it should be very straightforward. It's very similar to the solution here. It gives us t equals 8 seconds. Now I'm not going to write out the details of that because I don't have room. But we see that between the first and the third ball matches the velocity of the first after 4 seconds, catches it after 8 seconds. Now I don't know that this time will always be double this time. It happens to be this in this case, but that's probably because of some specific aspects of these functions that we could easily investigate, but there's no need. Okay, we have our solution. We expect the third ball to catch the first after 8 seconds. Now if we had ramps long enough, we could set this up and test it. Keep adjusting the ramp until the acceleration here is 30 centimeters per second squared, and this one is 40 centimeters per second squared. Then figure out how to get this thing started with a velocity of 40 centimeters per second and see if they really do match speed after 4 seconds and whether they're side by side after 8 seconds. Okay, now this scheme, this kind of solution is what you need to do many of the problems in Chapter 2. This is the way I recommend setting them up. I also recommend sketching and doing this yourself, not using a calculator, sketching accurate graphs of these functions. So we know, where the third ball, exactly where the third ball does catch the first. Now, that velocities match after 4 seconds. After 8 seconds they cross. So clearly this graph is way too narrow, way too steep. Also clearly the graph shouldn't be narrower than this one because the acceleration for this one is not that much greater than for this one. It should be narrower, but not that much narrower. And also this one should not be steeper than this one. So you need to sort that out. You need to use this kind of procedure, this kind of analysis in order to solve your problems. When you're done, after you've made your graphs, not before, go ahead and use your graphing calculator. Sometimes you need it. There are equations that can't be solved. If one of these is moving, let's say in accordance with a sine function, which might happen for a pendulum, and the other is a uniform acceleration, you can't exactly solve those equations. You can use approximation methods, but a calculator is not inappropriate in a case like that. For this situation, calculator is inappropriate. So I do recommend that you work this out and maybe kind of correct this graph, come up with a good set of graphs that match the solutions you can get with the equations. One other thing I'll say is, when do velocities match? Well, velocities are represented by slopes. So if I have, let's say, a curve like this and a curve like this, well, there's where the two meet, but where do they have the same velocity? At this time right here, now this velocity represented by the slope tangent line here, this velocity by the slope of this tangent line. Those tangent lines aren't parallel, they have different slopes, so you have different velocities. If we go to a later time, let's say here, this tangent line is going to be steeper than this one. Well, at some point between here and there, you would expect the two tangent lines to be parallel. Again, that marks the point at which the velocities match, at which the velocity of the one with the greater acceleration, which is the one with what's essentially the narrower parabolic graph, will begin to overtake the other. Very important to be able to interpret these things, so do be sure you give this plenty of thought.